Hello? Good afternoon. Can you guys hear me?
Yes, ma'am.
Okay, great. Thank you. Let's just wait for like 5 more minutes to see if other people are also joining. Hi. Let's just wait like 1 or 2 more minutes and then we can get started. It's not even like half of the people yet. That's why I'm saying. I think let's get started. Maybe people will join as time goes on. So I'm gonna start sharing my screen now. I hope you guys can see my screen. Okay. So I kind of want the session to be a little bit more interactive in nature. So if you guys have any questions at any time, please do unmute yourself and ask me the question. I might not be taking a look at the chat when I'm presenting my screen, only because it's a little difficult to operate the interface. But please, like I said, unmute yourself and ask me the question. So, good afternoon, and thank you for joining me today for the project session. In today's session, we will be seeing how to build a bilateral motor network that can be used under both normal and stroke conditions. My name is Sundari Rango. I'm a PhD student at Professor Srinivas Chakravarti Sir's lab, and I will be the one conducting the session today. So, just a few hours ago, sent you an email with all these particulars, like the paper that I'm going to be using as like the basis for the code that I will be presenting today, and also the actual GitHub code base that the paper uses, and also the collab notebook and details like that. So you guys can go ahead and take a look at those. And if you can, I would suggest at least open the collab notebook and download the file and keep it for now. We don't need to look into the code maybe for the next 10 to 15 minutes, but let's just, if you guys can get that ready, that would be great. Um, Okay. So yeah, we can get started. And also my email ID is there in the mail that I had sent you, and it's also there in the collab notebook that I sent. You guys can reach out to me at any time, even after the sessions are done, if you guys have any doubts in the code or in the paper, or if you want to discuss any project ideas that you want to pursue, etc. So o- okay, just give me a minute. I don't know why my PowerPoint keeps getting stuck. Okay, I'll just present like this. I'm hoping that it'll be visible enough anyway. Okay, so this is the brief overview of what the sessions today are going to be. Before we get started with the code, I'll just give a brief introduction on what is stroke and what is the problem statement that we're trying to tackle. And then after that, we'll be moving on to the coding session. Now, the coding session, I plan on dividing it into seven smaller sub modules, and I'm hoping by the end of it, you're able to train or you're able to code for a particular movement, create data set, and also create a neural network of an architecture of your choice and go ahead with training it. That is my aim for this session. Okay. Now, an introduction to the session. Now, stroke usually occurs either due to a rupture or a blockage in one of the blood vessels that supply to a part of the brain. Now, because of this, the neurons that get blood supply from that blood vessel starve and die. And unlike other cells in the body, they do not contain any energy reserves, and plus, they also do not have the ability to regenerate. So, the neurons that are dead cannot be replaced by newer or younger neurons, but the load that they were performing or the work that they were performing can be taken up by the other remaining neurons. This is the best case scenario that we can hope for. Now, due to the organization of the brain anatomy and the vulnerability of the different brain vessels or blood vessels supplying to different parts of the brain, the most commonly resulting problem after a stroke is physical disability and results in a condition known as hemiparesis. Paresis is characterized by a weakness in moving parts of your body, and hemi just means half. So, this weakness in making movements with one half of your body is called hemiparesis. Now, the treatment for this hemiparesis is basically physical therapy, and because they're motor in nature and mostly affecting the upper limbs, most of these involve hand movements of different types which the patient has to repeatedly perform before they can get regain functionality. Now, this is the problem that we will be tackling with our code session right now. Now, the reason why this is important is because I very quickly just summarized what the treatment scenario looks like, whereby once the patient gets admitted and their condition is stabilized, they're taken for physical therapy. But the problem comes in during this administration of the physical therapy itself. There's very many different types of physical therapy that is available for the patient, and because of this, it's not always straightforward or very intuitively known about what kind of therapy is to be given to what kind of patient. Now, another problem that comes in is this thing called as the window of plasticity. Now, right after a stroke, in the area around the region where the stroke occurred, there is a very high level of plasticity. That is, the neurons there are very enthusiastic about recovering, about trying to make sure that the person's functionality can be reset as soon as possible, and this is called as or weakly defined as plasticity, and this window of plasticity exists for a very short period of time, from a couple of days to about maybe a month. Now, because of this, only if we start the treatment as soon as possible, we can leverage this to make sure that the recovery achieved is as high as possible. Now, if we could have some sort of a system that can now replicate the human being that is affected and sitting here, then I can use that system to undergo these different types of physical therapy and then see which of those physical therapies is going to be the best in restoring the functionality to the maximum extent. Now, this is the problem that we're going to be tackling today in our coding session. So the first phase will consist of setting up the arm and the motor system. That is, how do I have an arm that is capable of performing normal reaching or goal oriented movements? And then using that, how do I simulate a synthetic data set? In phase two, once I have that synthetic data set, how do I then code for a MLP that is going to be used with this generated data set? Now, after that, I'm going to look at actually training the MLP. Here, you'll play around with different hyperparameters like different dimensions of each of the layers, different activation functions, different learning rates, epoch, etc., and basically see how the training itself varies. Now, once we're done with that and once we have the MLP ready, we will then introduce lesion into that network and see how the performance of the network is going to be different upon introducing stroke. For this, you'll use a UI element called as a lesion slider, which will help you pick which layer you want to lesion and how big of a lesion or a damage you can set up. After that, we can go into a rehabilitation clinic and see how we can provide retraining or therapy for such a network. Uh, just 1 second. Let me see if the PowerPoint thing works now. Yeah. Okay, cool. Okay. So now, does anybody have any doubts so far? Anything you want to clarify, or we can go ahead with the next part? Okay, cool. Then I'll go ahead with the next part. Okay, now, after we decide this is the problem statement that we want to tackle, we have to now create a data set because I'm not going to be using any complicated signals like EEG or EMG for the patient because with this network, we're only seeing how the behavioral part of the subject itself is impacted. Now, for example, in movement, specifically in movement of the arm, there are two joints that are moving. One is the shoulder joint and one is the elbow joint. So they have 3 degrees of freedom here. That is, they can move their elbow up. Sorry. They can move their elbow closer or away from the shoulder, having 1 degree of freedom, and 2 degrees of freedom at the shoulder. That is, again, moving your entire hand up or down, or moving it closer or away from the body. Thereby, you have 3 degrees of freedom, and each of those angles varies from 0 to 180 degree. Now, because of a stroke, this level of angle could be reduced, whereby the patients are not able to reach to different targets or different points in their workspace as well as they were able to reach to before. Now, this is the behavior that we want to simulate with our chosen network and see how we can make that network, once the damage has been set in due to stroke, how can we retrain that network in order to get back that range of movement again. So to do this, I have an artificial arm set up in a 3D environment on an XYZ coordinate space. Now the shoulder is placed on the x-axis at a particular point, xs, ys, zs defined arbitrarily by me, and I am considering my 3D space to look like this, where my x axis defines the left and right movements, y axis represents front and back, and z axis represents the top, the bottom. Now, on such a defined 3D space, I include two shoulders and arms and two eyes. Now, once we have set up the space, we now need to look into how do we actually create the data set itself on this. So, the goal that we're trying to tackle here, or the aim of the network, is if I present a target in this 3D space, the network or the hand should learn how to go from this position to an arbitrary goal position. To do this, we need to know what kind of configuration or what values of elbow and shoulder angles the hand needs to have in order to reach that location here. Does everyone understand what I'm trying to set up so far?
Yes, ma'am.
Hello?
Yes, ma'am.
Okay, okay, thank you. Yeah, so once we set this up, we need to, yeah, so we basically need to understand how to get the muscles or the angles that are going to be necessary for reaching to a particular position. Now, why is it necessary to understand what the angles are? Now, I know this diagram is very stupid looking, but please bear with me. Consider that this stick figure here is your arm. This point is your shoulder, this point is your elbow, and this point is your wrist. Now, let's suppose that the target position is somewhere over here. So, you need to take your hand from here to go there. Now, to do that, what is your brain going to do? There are two important parts in the brain that you need to consider here. One is the PFC, which is going to tell your motor centers where the target or the goal location is. Now, once the PFC has communicated that to the motor cortex then needs to send in electric impulses to the muscle. These are called as the muscle activations. Now, why is it necessary to do these muscle activations? Because the muscles are the ones that are controlling the angles. Now, look at this diagram here. You have three angles, one angle at the elbow and two angles at the shoulder. Now, let's suppose I want to bend the elbow from this point to somewhere over here, bringing it closer to the shoulder. So, for that to happen, my theta E needs to increase, needs to go beyond 90 degrees. Now, to do this, if you look at what happens in the arm, this occurs due to the contraction of a muscle that is present here and a simultaneous expansion of the muscle that is present opposite to it. Now, so the brain basically tells these muscles how much to contract or relax. So that's what this muscle activation value is going to communicate to the muscles, and those muscles will react according to those muscle activations, which then become translated into joint angles and hence hand movement itself. Now, because there's three angles that we have to control, we have three pairs of muscles that are defining each arm's movements, making it 6 into 2, 12 muscles for both the arms. 6 for the right arm and 6 for the left arm. So this is how the arm is going to be set up. You don't have to worry too much about the mathematical equations that go into this. I'm not going too much into it, but it's just a simple linear algebra with like rotation matrices and all of that. So you should be able to pick it up just by looking at the paper that I've given in the email that I had sent. Next is setting up the workspace. So we saw that we set up the X, Y, and Z axis as defined here. And we know how the arm is going to work. Now we need to define the target or the goal position itself. So to do that, we can't just randomly take any point that is given in the 3D space. Why? Because we have only the arm that is fixed at a particular point, that is a shoulder fixed at a particular point, so it can only reach to the points that are going to be less than or equal to the length of the hand itself, and if it wants to reach to targets that are beyond that, then it needs to move the torso. But for now I'm not considering a torso itself, so I'm restricting the movement to be only within that radius. So although this is all of the points that I have, this whole space here, these are the only points that are going to be reachable by the arm. Now, inside this, only certain points are going to be visible to my left eye and only certain points that are going to be visible to right eye. Now, I need to select points that are going to be visible to both eyes. That results in a workspace like this. So, I have my 3D space, I have my targets, and I have my arms. So, I just plug these targets into my equation system, and that will give me the angles or the muscle activations that are going to be necessary for the arm to reach to that target. So now that we've set up the workspace or the data set, we can directly use that data set now to train the network. Do you guys understand things so far?
Yes, yes, ma'am.
Okay, just one second. Someone had asked me what if you had collected the real data from patients, then what is the issue from synthetic data? No, we're not collecting real data from patients. This is a very synthetic network, so because of that we're not uh, so the point of the network is not to be as dynamically realistic as necessary from the patient. The only thing that we're trying to replicate in this network is, if given a target, are they able to make certain arm configurations in order to reach to that target, and that ability gets severely compromised with stroke. So for this, I can't directly get data from the patients because patients' data is already going to be compromised because of that problem. So I can't train a network on that and then build something on that. I need to first simulate what a healthy model is going to look like. So that is the reason why I'm doing synthetic data generation. But all of the equations that I use, etc., are all equations that are used by robotic systems also. So they're not completely, what do I say? They're not completely artificial equations that are not useful for anything. So does that make sense? Arup, I think that was your question. Does that make sense? Okay. Okay, so this is the introduction so far to the code. So I think we can now move to the actual code itself. Just one second. Yeah. Okay. So this is the session outline. First, so far I've told you how to set up the arms and generating the data set. Next, we'll see how to code the MLP for use with the generated data set. Now, I hope that you guys downloaded the Collab notebook. So I'll be putting you guys in breakout rooms in just a little bit after I explain how you code for an MLP. And there I want you guys to try different architectures or different training paradigms and see how the MLP is training with that data set. Now I'll just go over the code blocks until we reach to that point. So this is just a general purpose thing. Just one second. Oh, yeah, I'll share the notebook. Uh, Please kindly like download it and have a local copy or upload it um in your in your Google Drive and access it from there. If you directly make changes in that, that's going to interrupt the code flow for every participant there. So please be a little careful with that. Okay, so the first block here is just for importing dependencies and libraries that are going to be used by the rest of the code. And it's mandatory that you run it so that the modules will function properly. And once you run this part, then you go to phase one. Here in this part, you have two sets of codes that are going to be used to set up the arm and the space. So the first code block here uses something called as inverse kinematics. So if I give you a certain set of angles, and from that angle, if you find out the position that it would lead to, that is called as forward kinematics. Now, if you do the reverse, that is called as inverse kinematics. So this code block here is basically just to set up the equations that are necessary for this. Then once this is done, you have the setting up of the workspace itself, where it basically filters the points according to distance and whether it's so here another important point that I forgot to mention is we're only considering the points that are going to be in front of the hand and not the ones behind the hand. So we're also restricting it in that way. And then after that, we're going to restrict it to be visible to both the eyes. That's what this one does. Okay. Now, in addition to this, we also do another thing called as generate bilateral stereo data set with conditions. Now we know that there is a target that I'm going to place somewhere in the 3D space and I have two arms, but there's only one target. So which of the two arms do I need to use in order to reach that target? That will be supplied by something called as hand selection parameter. If I send this hand selection parameter to 1 1, then I have to use both of the arms to reach to the target that I have placed. But if it is 0 1, then only the right arm will reach while the left arm will be at rest, and vice versa for 1 0 condition. However, if it is in 0 0 condition, then neither of the arms will move and they will be completely at rest. This is because if you remember the types of therapies that I was talking about, there is one thing called as constraint induced movement therapy, where only the affected hand is moved while the unaffected hand is not moved. But in bimanual therapy, both the hands are moved together. Whereas in mirror therapy, only the healthy hand is moved and the affected hand is made stationary. So, in order to incorporate those conditions, we have these things called as hand selection parameters. So, with these hand selection parameters in mind, whatever points I generated in the feasible points function, I then send it to this data set with conditions function, and it will put up the data in this condition and give it to me back. So that's basically what this program does. And the this is just for plotting to visualize how the arm is moving and um, how the workspace looks like, etc. Okay, so now we're ready to generate the data set using the arm that we set up and the 3D space that we set up. So to do that, you can run this code, and it will show you the number of points that were considered and the points that and how those points reduced after each type of filtration. And this is a visualization of those points itself with legend given here. And the next is basically a simple example of the arm trying to reach to the target, and the title contains the elbow and the shoulder angles that are made. So, until now, if there's any questions, you can ask me, or we can move to the next part. Okay, I'll move to the next part then. Just one second. I'll just close this. Okay, so next is going to be coding of the MLP. So just forget about this function. Don't worry about this function. I want you guys to concentrate on this simple integrated brain model and this bilateral split brain model. So here I have two MLPs with very different kinds of architecture. In the integrated brain model that I have a very linear structure like this, where I have an input layer that projects to two hidden layers, and then that in turn projects to the output layer, and that output layer basically contains the muscle activations that are necessary. Whereas in the bilateral split brain model, the input layer is split into two halves, one for the left and one for the right. Now these two separately go into the shared hidden layers, which then again branch out into two output layers, one for the left and one for the right arm. So that's how I have defined the two things. And the next thing is the train function itself, which is going to help you train whichever network that you choose out of these two. So I'll now split you guys in two groups, or in three groups maybe, and you guys can go through the code so far. And what I want you to do is pay attention to the blocks under coding the MLB. Now there, under class simple integrated brain and class bilateral split brain, I want you to first go through that code and try to understand if you're able to try to see if you're able to understand how the MLP looks, what the different layers do, how the each different layers are connected to each other. Then after that, just with pen and paper, just to come up with an architecture that you would like to try. Like, you must have seen a lot of architectures that look like this. Most of the deep neural network architectures look like this, but this is a little different. This one is a little atypical, and most often structures or architectures don't look like this. So just go over the two and just draw in pen and paper like what kind of architecture that you want to try. Then after that, I will come and visit like each of your breakout rooms, and I can help you guys with like coding it and training it, etc. Does that sound good? Okay, I'm
Are
going to
you
assume.
able to
Yeah.
give the examples of the architecture like your screen went off?
Oh, sorry. Sorry. Yeah. Can you see my screen now?
It's loading. Yeah, now I can see.
Yeah, okay. So this example that I'm highlighting, this is a slightly atypical architecture for a deep neural network, where the input and output are split, whereas only the middle regions or middle layers are shared together. This, if you think about it, is very similar to how the brain is. The left eye and the right eye separately project to the brain, and the brain itself processes the things, and then they separately project to the left and right hand. Whereas what is typically seen in deep neural networks is this sort of an architecture. So you guys just go over the code, and I want you guys to first like write down a architecture like this, and then see if you can code for that architecture that you want to try out. And I'll start visiting the breakout rooms in like 5 to 10 minutes and help you guys in coding it itself. Does that make sense?
Mhm.
Okay. Okay, cool. So I'll put you guys in breakout rooms now. Hello?
Yes, ma'am.
Hello? Can you guys hear me?
Yes, yes, ma'am.
Okay. Do you guys want to tell me what you guys are looking at or what you guys are trying to do? Are you guys working together or separately?
I was looking at the code, ma'am, like simple integrated and bilateral little model.
Okay.
One thing I wanted to ask, ma'am, that like uh, we have some stroke patient,
Hmm.
okay, and we have some healthy candidates here, okay.
Okay.
We are generating some healthy like robotic arm in the first blocks.
Hmm.
And then what we are doing, we are predicting the angles, like what angle should be there to from reaching to target. Okay, I have my arm here, and after I am reaching the target, how my angles are changing. So
Right.
that's what I. So like at, at the end, what is the benefit of this? Like stroke patients cannot move their arm. Uh, so
Yeah,
what
but we can see
final aim here?
how, yeah, but we could make them learn. So, how do
Yes,
we design like a curriculum or a training paradigm so that they can get better at it? That is the point of the
okay,
network.
so we are doing like this with healthy patients, like healthy
Yes.
persons, or the
Huh,
robotic synthetic data, that how
huh,
much angle should change from going on to the target,
huh.
and then based on the change of angles, we can give therapies to the stroke patients. That is
Yes.
our aim.
Yes. Exactly.
Okay, okay.
Okay. Anybody else? Like, how are you guys finding the code or any doubts or clarifications that you have? Yeah, Arup?
Yeah, ma'am, I'm just sorry. Sorry, I'm just out of station. I'm just participating over my
Okay.
phone, so I could not
Look at the
apply the
code.
code.
Okay,
Code.
okay, okay. I understand. Okay. What about the other two? Guna and Bhavna going through the code. Okay. Anything that you need help with? Anything that you want to clarify or anything?
So at the end, ma'am, what our model is learning here, like changing angles, like from reaching to target, what should be the change of angles with this neural networks.
Okay, so what happens after a stroke is the
Yes, ma'am.
degree that the joints can move is going to be reduced. So, what physical therapy will do is slowly, you try to increase that level of angle that is usable by the patient. So, slowly increase from that reduced value. But now we don't know for a given patient, we don't know what type of therapy is going to bring that in. Is it going to be useful for them to move both the arms together, or is it going to be harmful for them to move the affected with the healthy arm? So to see all of that, if we have a network that is able to do this, able to simulate this, and we can try and see what happens if I move just the affected arm, whereas if I move the affected arm with the healthy arm, then how is the performance of the patient going to be? Then using that, I can just apply the one that is recommended by my system. That is what the network is trying to do, or that is what you hope to do with your network.
Okay, like there is a function train brain here in the code.
Hmm.
Uh, so they, like how we will know that it how it is affecting the patient itself. Like we have some synthetic arm here in the previous code.
Mm.
But how we will know that our therapy is working better or it is not working better? Like,
So we
what
will
is the pro-
measure the, yeah, so we
mm,
will measure the distance between the hand and the target. So if it's able to reach to the target very closely, then we can say that the arm has performed better at one versus the other. So with one kind of therapy, if I was only able to make an angle of 130 degrees, so I was able to reach within like 5 centimeters of the target. Whereas with the other type of therapy, I was only able to make 120 degrees. So I was able to reach about 10 centimeters from the target. Then obviously therapy one is going to be better, right? So that is how we'll try and figure out.
thank you.
Okay.
You have a good synthetic data set, so that is working for the healthy, that is working as a healthy control, right? So, but when a stroke patient comes, so how do you measure what is the current status of his arms, or how at what degree these arms can he move? So, how is the comparison is done?
So for to do that, there are certain movement assessment scales that the clinicians will use along with imaging data. So by doing imaging, like MRI imaging, the doctor will try to understand where the stroke is situated. Once we know that, we will know if the patient is going to have a movement problem or a walking problem or a language problem. Now, once that is done, we'll have a battery of tests specifically for that. Like if it's going to be a movement problem, then for hands we have something called as wolf motor function test or a Fugel-Meyer assessment test, where the patient is made to perform different movements, and how they're performing the movement is graded by a physiotherapist. So by doing that, we know how well they're able to, or what all difficulties they're facing with making movements.
So assessment is done by manually or by some imaging method or video collection from the videos.
We're actually developing, like, we just finished developing a system that can do it using videos, but in the standard clinical setting, it's done by a person, by a physiotherapist.
Okay, okay, thank you.
Okay. Okay, so you guys maybe keep continuing. I will be back, and at that time, maybe we can look at the code itself. Like, if you guys are working with the code, like, what are you guys doing, etc. Okay.
Okay.
Hi, did one of you ask for help? I saw a notification pop up, but
Yeah.
yeah,
I want to ask, so the task was to think of the such architectures like the two examples you gave through the code,
yes, yeah,
and we are supposed to think one another example through which we can build another kind of architecture.
yeah, or just a simple thing of just increasing the number of nodes in each layer, or something like that. Just so that you can understand how you can code the neural network with this and all that. Because I think most of the participants do not have training with this kind of coding. That's why.
Can the reflex section be included in this?
Reflex action. What do you
Like
mean?
if I touch a hot vessel, so there is an input. Like, can we include the stimulus from outside?
Yeah, but
And
that is what you're doing, right? Like the target position is also given from the outside as an
Mhm.
input, and then it tries to reach to that. So when you say reflex action and like temperature, those kinds of sensors are not present in this um, network. So if you wanted to, you could expand the input layer. So currently it gets four on each side, four on left and four on right. You could maybe include to have five for each side, and the fifth one could indicate some sort of a temperature parameter. So if that value is in the positive, then that means it's hot, but if it is zero, then that means it's an object that's at room temperature and you can touch it. But if it has a negative value, then it's a very cold object. So depending on what that parameter is saying, now the you can structure the data set so that if it is a very hot or a very cold object, the hand will not move to touch it, even if the hand selection parameter is instructing the hand to touch it. Whereas if only if it is at room temperature, either 0, 1, -1, 2, -2, then it is at room temperature or close to room temperature. Then it could go and touch the object. You could try something like that, but that will involve little bit more tweaking of the code in both creating of the data set and also in the network itself. So
Okay. So
y-
in
y-
the code, are we supposed to tweak here anything, or are we supposed to just give the example to you?
no, you can try tweaking it.
In the
Just
training
in
the
the
MLP section?
Yeah, that is for the determining or declaring the network itself. But your thing of having another uh, parameter in this, you will need to tweak it in just 1 second. In the function, generate bilateral stereo data set with conditions. So there I've included, right? Like if you look at the for loop in line number 165, there for each 1 1 condition, 0 1 condition, 1 0 and 0 0 condition, I'm saying how the arm is going to be, right? So
Mm-hmm.
you can now include another temperature condition and then expand this. That is where you'll need to do the tweaking. Once you've done that, you have the data set ready. So then you'll have to move to your architecture in either the class simple integrated brain under coding the MLP in the phase 2 section, or in
Mm-hmm.
your bilateral split brain, and instead of having the input size as 4, you will make the input size to be 5. That's how you'll have
Okay.
to do it.
Okay.
Yeah.
Okay.
Okay, so go ahead and try it, and I'll be back again to see how you're getting ahead with it. Okay?
Hmm. Okay.
Anybody else? Umarani and Shivani.
Yes, ma'am. As we told, I changed that structure under structure
Hmm.
input layer. I have changed it 5.
Okay.
But I am getting error, ma'am.
Yeah, because currently the input only has four, right? It only has the
Yes, ma'am.
XYZ of the target and whether
Okay.
I should move that arm or not. So if you're going to change that, then you have to change the data set itself. So instead of that, if
Okay.
you want to try playing around with the numbers, you can try with the
Okay.
other layers after that. Or you can try the changing the output neuron number in the layer, in
Okay.
the first layer. Yeah.
Okay. Please,
So you
ma'am.
can
We'll
try
try it.
those.
Yeah,
Yeah.
thanks.
Shivani? Okay, you guys keep doing it. I'll be back in a bit to check on you guys. Thank you. Hello?
No,
Yeah, hi, Krishan. Have you tried like playing with the code in any way?
yeah, yes, ma'am.
Sorry? Hello?
Yes, ma'am. Yes, ma'am. I was doing it.
Okay. Can you show me what you've been trying to do?
Yes, ma'am.
Okay. So you tried training it, right?
Yes, ma'am.
Okay. Did you try changing anything or you're going with the same thing?
No, no, no. I haven't changed anything. But I
Okay.
was, but Indian accuracy was not so good, so I was like looking for the problem here.
Uh, Sorry, what was not looking too
Like
good?
accuracy at the end was only 40% here, I think.
No.
I
So
was,
this is with lesion.
yes,
So, okay. So you went through the other stuff also?
yes, ma'am.
Okay. Do you have any doubts?
Yes, ma'am. Like we have two models here, but
Hmm.
here is very less. I think it should work good.
Hmm.
This one,
Hmm.
because error rate is very low.
Hmm.
I'm not sure about the lesion one. The accuracy is not so good.
Yeah, maybe
Mm,
sometimes the lesion might be too big that the network is just not able to recover at all. So you can try with a very small lesion, or you can uh, otherwise try to make the size of the network a little higher and the lesion to be a little smaller so that when you try to retrain it, it has some sort of like thing to recover with.
okay. And like there are two models. One is integrated brain and one is
Yes.
split brain. So
Yeah.
like it is how we know that it is only training the left part or right part of the brain.
No, it is going to be training the entire network.
Entire
Currently, it's
network.
not, yeah, it's not
Yeah,
fixed like that. But you can fix whether you want to have the data to only include movements of the left arm or only include movements of the right arm. Now, because of that, if you have 1-0 condition where only the left arm is moving, then it basically means that the right arm is not doing anything. So it's just staying put at whatever position it's at. So it's not really learning anything new. So in that way, you could say that it's not training. But you can try with, there is a parameter called requires grad, like nn dot linear dot weights require requires grad equal to false or true. It's by default true. It's only if it is true, the gradients for that layer will be calculated and back propagation can be done. Now, if you set it to false, gradients will not be calculated and back propagation will not be performed. So you could try with something like that and see if you just freeze one layer, etc., what happens.
okay.
Okay, I feel like you already finished the session. I don't have anything else to show you.
No, I just then I cannot do fast. Then I was like trying to understand that what is happening here.
Okay, okay, got it. Okay. Okay, continue then. I'll be back in a little bit, okay?
Okay, thank you.
Anybody else? Oh, I guess Arup, you're on your phone. And Bhavna, anything you would like to pitch in? Anything you want to clarify, etc.? Okay, so I'll give you guys like maybe 10 more minutes and then I'll close the breakout room. So we'll come back to the main session and we can talk again about anything that you guys found interesting, etc. Okay, see you guys in a bit. Hello? Hello, Meenakshi, can you hear me? Hi. So are you able to follow with the code? I don't know if you were present when I gave the problem statement itself. Anything you want to discuss? Anything you want to talk about? Okay, you can go through until about phase three. After that, we'll come back again into the main meeting room, and all of us can go over it together. Okay, I'll see you in a bit. Bye. Hotel where? In the code, it'll say no, like phase three, training the MLP. Until then, you could take a look. After that, we'll come back again into the main meeting room, and we can go over things after that. Okay, cool. Hello.
Mm.
Yeah. Hi, Varnika. How is it going? Are you able to get what you were trying to do?
No, I'm a bit lost. Like I'm
Okay.
able to understand what's going on, some bits of it, but
Okay.
I'm not able to like include what I and how I want. I mean,
Okay. Do you want to present the screen to me and show me what you're struggling with, or you want to try a little bit more?
depends if we have time.
Yeah, yeah, we have time. Tell me.
So, okay, so I'll join through my laptop then. Actually, I
Yeah.
was using both the devices. Give
Okay,
me.
okay, sure. Yeah, sure. Uh, Uma, maybe you could tell me in the meantime, how is it going for you?
Yes, ma'am. Actually, I also tried, but I couldn't able to get the concept, ma'am.
Okay, do you want to
I am
present the
not.
screen and show me what you're struggling with?
Uh, uh, just a minute, just I want to clarify, ma'am. Just I want to clarify one thing.
Hmm.
Under the structure, should we change this number of inputs, or that's what I didn't understand. Actually, I have copied this code and pasted it in this chat GPT.
Okay,
That it is showing that we can add what is it? Split brain architecture, like that error gated split brain architecture. We can go to a error gated split brain architecture like that is showing. But I
okay,
couldn't able to understand the concept now.
okay, okay,
You could be able
okay,
to tell me once again, ma'am. Once again, I'll just try it once again.
okay. I'll present the code. Just one second.
Yes, yes, ma'am. Yes, ma'am.
So I don't want you guys to like struggle too much. Also, you can just try
Yes,
a
ma'am.
few things. Like
Yes, ma'am.
say here,
Under
I
phase two, yes, ma'am.
yeah. So I have like hidden dim equal to 64, right? You can try
Yes.
increasing this value. And you can
Okay.
also try adding more layers like shared layer 1. Instead of just having
Okay.
that, you can have shared layer 3, shared layer 4, all of that.
Okay.
And you
Yes,
can
ma'am.
try and see how that is going to change my training. You can try something like small like that. This is
Okay, okay.
just to give you a little bit of experience with coding for MLPs. That's all.
Yes, ma'am. Okay, I'll try it.
Okay.
Yes. Thank you.
Yeah. Yeah, Varnika, you can show me your screen.
Yes. I'm finding the sharing option. Give me a second. I'm sorry, where can I share my screen from?
You're on Zoom, right?
Yeah,
There'll be a option in the middle of your screen at the bottom called share. You can just press that and it will tell you.
I could see participants, chat, reactions, and more. Then
Try clicking more.
captions, ask for help, whiteboard settings, stop incoming video. That's it.
Oh, okay. Okay, then maybe I'll try presenting the screen and
Yes.
I'll tell you. Yeah. So you might need to do it over here. So you have X list and Y list, right? So here on top of this, you can have another for loop. Uh, then, mm, you can have temperature is equal to np dot array of uh, minus 5 comma 0 comma 5. Okay, and you can have for temperature temp in temperatures, and then you can have the for loop here. So now if temp equal to 0, then you have this normal condition whereby it is going to behave with respect to what your this thing condition is hand selection parameter is telling you. Along
Mm-hmm.
with this, you can also concatenate the temp parameter in all of them. Okay. Fine. Now, if otherwise temp equal to 5 or temp equal to minus 5, then you'll just have both the arms at rest at all times. So this thing will be the same, but here you'll need to make it as rest R, rest F. So that if it is too hot or too cold, the arm is not going to move towards the target and it's just going to be at rest. But if it is at room temperature, then it's going to um, go and read. Now you could also try and expand this temperature thing to include -1 comma and +1, so that if it is room temperature which is 0 or close enough to room temperature, then
Mm-hmm.
you can reach to the thing. So maybe you could try something like this
Okay.
and then see. So once you do this, I'll maybe put this code in the chat box. I don't know if it will accept so many lines. So I've put, okay, it's too many lines.
I just have to copy the for loop, right, and add the for condition.
Yeah, below, I mean above. Yes, exactly.
Right
So,
below the X list comma Y list, we are defining the array there, and then below that only we'll start the loop for temperature.
yes. So you only move if at or close to room temp. Okay. And in
Mhm.
this condition, we target either to hot or to cold. Okay. I think since I've shared the notebook to you, this code will anyway be accessible to you also. So now, once you finish this, you will also have to make changes in a few other places. Like, okay, see, so here, the input dimension is going to be, one second. Yeah, input dimension is given as 8, but now
Mm.
your input dimension is going to be 10.
Yes,
Okay, and same way here also, where you split it as 0 is to 4 and 4 is to 8. Instead, you'll do 0 is to 5 and
5 is
5
good.
is to, yes, exactly. Okay,
Mm.
so
Mm.
those things you'll have to change. So you try changing those things and see how the network is learning. Okay,
Okay. Okay.
okay. Okay, so you guys continue with this, and maybe in 5 to 10 minutes, I'll close the room and put everyone back in the same room and we'll discuss further. Okay, thank you. Hi. I hope you guys tried something during the time that was allotted. Does anybody want to discuss anything in particular? Like anything that you guys tried or you want to try, anything like that?
Yeah, the changes which you asked I bought, and the dimension, input dimension, output dimension, and all I should change in the
Yes.
training MLP section. So here the input dimension, batch size, vagera, all will increase accordingly.
Batch size should be okay, but your input dimension you'll have to change. So when I say input dimension, so each input is going to now be 5 into 2, while the batch size denotes the number of such inputs that is going to be presented to the network in one shot. So that you don't have to change, but you have to change the input dimension of the network itself.
Okay, so like currently input dimension is 8, so I'll change it to 10, and hidden dimension would be 128 then.
That is up to you. You can try with just the 64 one that is given here, or you can change it as 128, or you can try any other intermediate number. Or
Okay. So input dimension will be 10, hidden dimension I can keep it as 64 itself, and
yes,
output dimension will stay as 12 only.
yes,
Okay, I'm still facing few errors, but okay, I'll see.
okay, okay. Okay, I'll just go over the code a little bit so that everyone can understand. Like, I'm not able to get the understanding of what everyone's background is. So I'm just going through the network, like how the code and the syntax work so that you guys can make your changes yourself. And also give a little bit of introduction to what Varnika is trying to do. So Varnika wanted to try and see if we can include reflex actions in the data set. So reflex actions here that you wanted to try was if it's a hot object that you're touching, then you take off your hand right away from it, or right? Or if you know that it's hot, you try not to touch it anymore. So in order to do that, along with the conditions, hand selection conditions that we've included here, we decided to include one more parameter that is going to denote my temperature. So here I've taken five different types, 0 denoting the room temperature and -1 and -5 denoting colder temperatures, whereas 1 and 5 denoting hotter temperatures. So now the network is going to be forced to only reach to targets when they're at a temperature of -1, 0, or 1. That is either if they are at or close to room temperature. Otherwise, the target is either too hot or too cold. So it will try to avoid it. So regardless of what the target is and what the hand selection parameter is, the network is going to just stay put. It's not going to make any movements at all. Whereas if it is at or close to room temperature, the network is going to move according to what the hand selection parameter is telling the network. So now, once she has such a network, she'll need to also make changes in the network itself, because currently the network is set to accept an input size of 8 and give out an output size of 12. But now her input size is going to change from 8 to 10, which means the input dim here, that will need to change. Along with that, this is for the integrated network. But if she was using the uh, split brain model, then here this is going to become 5 and 5. So here she will need to change this to 5 and this to 5. Another thing is, let's say you want to change the dimensions of the hidden dim, that is of the hidden layers here. Now, I just want to explain a little bit about the syntax of this. Now, how this or what this code basically denotes is self, which means it's referring to the neural network that is defined here, dot name of the layer is equal to, it's a neural network of linear type. That is, it just has one layer instead of using like a sequential thing where it's going to be multiple layers defined in one way. And within the brackets, you're going to tell the size of the input to the network and size of the output from the network. Now, the input from this layer, or sorry, the output from this layer is going to go as input to this layer, which means we need to maintain consistency here. So the output size here needs to match the input size here. Here it's not a problem because all of them are going to be equal to hidden dimension. So when you're changing the network sizes, please make sure that you're able to maintain this consistency. So this is just going to use matrix multiplications. So if the matrix sizes are not compatible with each other, then multiplication operation cannot be performed. That is the reason why this consistency needs to be maintained. Next is these activation functions. So this is basically what you will apply to the network in order to introduce non-linearity to the network. So for that, you can either use a ReLU function, sigmoid function, tangent function, etc. There's also multiple other types you can decide based on what you want to try. Yeah, so this is where this def init function basically is where you're defining the or uh, declaring the input, declaring the network. But you're not really, so you can, if you think of a neural network like a graph, this is where you're telling what each node in the graph looks like. Whereas in the forward function, you're basically trying to see how each of the nodes that you defined in the above function is going to be connected to each other. So here, what you'll do is you'll get the access the input here, and then you will pass it on to the first layer in this hierarchy. And then the output that you get from that, you will decide and pass it on to the next layer, and then so on and so forth. So here you cannot do anything to change the sizes. If you want to do that, then you'll have to do it in the init function. Here, it's only in how you're going to pass the input from one layer to the other layer. Then the next is the train brain loop. So the train brain loop is going to take each epoch in the number of epochs that we defined and run the operation within this for loop. So within this for loop, it takes each input and the target output. Here, targets do not refer to the targets in your workspace, that is goal position, but rather the targets here refer to the desired output for the given input. Now, this input is given to the model, and from the model, we get predictions. These predictions are then compared to that desired output, and a loss is calculated. Then we need to propagate that loss backward and use that loss to optimize or adjust the weight. Then after that, the rest of the function is just to store the losses that were achieved across all of the inputs for a specific epoch. Then the reason why there is a history and everything is because you can store it in that so that you can later plot it and see just to look at the plots. Like when you run the loop here, because it's only 20 numbers, you can just take a look at it from the screen here, or you can scroll and look at it. But if you increase the epochs, sometimes the epochs need to be some thousand values or something, it's not going to be very easy for you to just take a look at the screen and find out how the training is progressing. So at that point, it makes better sense to plot those values and see what happens. So then next, you have something called as the validation phase. Here, now we got the data set that we generated in step one. But in order to make sure that the network is not just simply mugging up the data, but it's actually trying to learn the patterns within the data, we have something called as training data set versus validation data set. So for this, what you do is you take the data set that we generated, and an X percentage is going to be used for training, and the rest of it is going to be used for validation, where the network will be validated, or the training that you performed here, how good is it on data that the network has never seen before? That is what your validation phase is going to determine. So it's going to do the same thing, that it's going to take the input and the corresponding desired output, give the input to the model, and then compare that prediction from the model with the desired output in order to look at the loss. Excuse me. So along with the training loss, you'll also calculate this validation loss and also include that. And that is also what is displayed here, training error and validation error. So your hope should be that training error and validation error both need to go uniformly in a decreasing phase as the training progresses. So that's what you're trying to do. And here, this is where you're trying to load the data set, split the data set into training and validation uh, values. And then after that, you're giving it to the split brain and the integrated brain. When Varnika changes her input dimension, she'll also need to change it here to 10 from 8. Then you are calling the train brain function, and then you're giving the model that is to be trained, and the training data set, validation data set, the number of epochs that you want to train it for, and the learning rate. So that's what you're trying to do. Now in the next phase,
Mom,
yeah,
I'm getting error here.
what error?
Mat 1 and Mat 2 shapes cannot be multiplied. 32 into 3 somewhere and 5 into 32.
Uh, Okay. Can you tell me whether you're facing the problem in the integrated network or in the bilateral network?
Mm,
Can you just paste the error message in the chat box?
yes. It's giving me runtime error.
Yeah, I understand.
I've shared the chat.
Yeah, I'm going through it. Uh, okay, so this is in the split brain model. Um, it's, I think, because somewhere the network definition has gone wrong. Um, can you, you can see this def init function, right? That I'm showing on the screen.
Yes.
Can you paste that def init function that you modified now in the chat box?
Huh. Okay. Uh, it's in the chat. The
Yeah,
size problem. So I'll uh, paste before the forward function.
yeah,
I hope it's visible.
yeah, it's visible. Just give me a minute. Okay.
I'll share the section after the definition of forward.
Yeah. Can you also share, one second, this part of the code, this part of the code, line number 22 to 24
With section phase 3.
in,
Okay.
yeah, phase 3.
Initialize training.
Yes.
Okay. Yep. Shared.
Whatever you're doing is correct only. Are you able to share your screen now or no?
I'll try.
Okay.
Like, is it like I think you have to stop your screen sharing.
Yeah.
Okay. I'll Google it. Meanwhile, you can explain. I'll Google how to share the screen. I think
You're
I'm
not
using
getting
browser.
access.
That's why I'm using from browser.
Or Zoom, you mean?
Yeah, I'm using Zoom browser. Is it okay?
That should be okay. I don't know why it's creating an issue. Okay, anyway, I'll just explain the rest of the code to the
Yes.
others.
Yes, ma'am.
And once we put everyone in breakout room, maybe I'll come back again to you. Okay?
Yes.
Yeah. So if you guys then have this part done, like until the training part done, then you can start introducing lesion. Now, the reason why within that lesion function, we're declaring the or defining the networks again is because we need to now incorporate the networks to be able to accept these things called masks. So the masks are the ones that are going to define my stroke. So in the brain, as soon as your blood supply stops, then the neurons are going to start starving and dying. So if we make an analogy to the neural network, then we can say that once the neurons die or once they have a stroke, then those neurons no longer contribute to the functioning of the brain. So it feels like all they're communicating with the rest of the brain is zero. So in order to do that, what you will do is you will define an array which is going to be of the same size as the layer that you're going to produce a stroke in. Now, if you want no stroke, then you will produce a mask with all of them having the value or array having the value as 1. Whereas now, if you change it so that the second one, fourth one, and sixth one, the value is 0, then this means you've created a damage of 50% damage or 50% lesion. This is because you turned off 50% of the neurons in the network. So this is what the masks are going to do. Now you're going to define such a thing for each of the layers so that each of the layer can now accept the stroke condition. Now once you do that, then you will train the model again now because this is going to now train this model with inclusion of these masks. So I slightly, I think, train that for a little longer. Just a minute. Okay, so as it gets trained, so in the next phase, what we will do is we will start introducing an interactive lesion slider and evaluation over workspace. So now, once we know that the network is trained, how do we verify if the training is correct or not? Because if I give a target of say 0, 0, 1 and the network is going to tell me some sort of value like zero point 0.5 comma 0.75 comma 0.25 comma 0.35 like that, like some values between 0 and 1 and an array of size 6, then how do I know if that is the correct value for that target? Now sure, for training data set I will know because for the given thing I know the desired output and I can just directly compare it with that. But what about for targets that I've never seen before? What if it's a completely new target? So for that, I will need to converse those output that the network is going to give into target position and then compare that position with the actual target itself. So to do that, you will have to have equations set up to do this. So that is what this function workspace position from function from muscles is going to do. So once it evaluates that, then it's going to become a lot more easier for the network to start or for us to compare the performance of the network. So once we do that, the rest of the functions here is set up just to allow the network to accept the lesion and also see if we can create a simple UI element that's going to accept this sort of a lesion condition. 1 second. It's almost done training. Yeah. Mm, Okay, so this is just to define the UI elements and stuff. Then after that, we have this lesion slider thing. So here, this is going to denote my plots that I'm getting. So here, this is a 3D plot, and the title of the plot basically tells you what this plot is supposed to denote. So here, the first word here, split brain or integrated brain, tells you the model that I have chosen to create a lesion in and the layer that I've created the lesion in. Along with that, I also displayed two other things, which is the percentage of lesion that I've created and whether this plot is for the left arm or the right arm. Now, once that is clear, we look at the actual plot itself. Here, each of the dots given in this 3D workspace denotes a target in that workspace, and the color reflects the amount of error that is experienced by the network when it tries to reach to that target. A more yellow color means the network finds it very hard to reach to that target, whereas a more blue color indicates that it's much easier for the network to reach that target. You can include you can select the type of or the layer of that you're going to create a lesion in and also the amount of lesion that you're going to create by sliding the slider here. So I'll put you guys in breakout room now. You can try to run these next few blocks that I've told you about and then see how it is impacting the performance of the network. Okay. Any questions so far? Okay, so I'll put you guys in breakout rooms then. Hello, Arnika. Did you figure out how to share your screen?
Yeah, so I googled it. They're saying that host might have hidden that option. So can you check if you restricted the screen share option?
Hmm, no, all participants can share it.
Okay.
Okay,
I
are you using Collab or are you running it in your local system?
collab I'm using. I mean,
Okay.
I created the copy of the collab for myself.
Okay, just
I
send
will
me the
share.
link on the chat. I'll open it on my side.
I'll share the collab.
Hmm.
Okay. I'll share through your email.
Or you can put it in the chat here. I don't mind. Either, whichever is convenient.
Okay, I'll share the link in the chat then.
Hmm.
Suppose one வேகமா போட்டோம்னா 50
I've shared it.
Yeah, I'll open it. Just a minute. Yeah, this is the code, right? Okay, I'll try to figure out what the problem is. You also keep trying, and I'll come back in like 5 to 10 minutes with and we'll check back again. Okay?
I can run the lesion part. It won't
Yeah,
affect, right?
it won't affect. Yeah, yeah, you can do it.
Okay.
Yeah,
Okay.
thank you. Hello?
Yes, yes.
Varnika, I figured it out, but it wasn't a problem in the network thing. I'll just uh, putting in the chat how we should modify the um work. I mean, data set generation thing. So instead of having xlist dot append np dot concatenate x square bracket one close square bracket and then temp, doing it this way is creating a better list. I think it's because of the v stack thing that I'm doing later on. So
Which
maybe you can
section are you talking about?
in under function generate bilateral stereo data set with conditions under phase 2,
Phase 2. Okay, okay.
that
Generate
for
pilot.
loop that you generated. Yeah, so instead of using that x list, do the try the thing that I've put in the chat box. Try it like that in that format. That should work. Okay, I mean it's working for me, it's training for me, so
Mm-hmm.
just check if that is working. Okay.
Okay.
Okay,
Okay.
so I'll just be back. We'll maybe take 2 to 3 minutes, and then after that I'll put you guys in the main room again, and then we can conclude the session. Okay?
Did you include the update in your notebook or in my mine one?
No, I did it in a copy of it. I've not done it in yours because
Okay.
since you're also using that lesion slider, I didn't want to mess with your code.
Okay. Okay. Cool.
Yeah. You can just try using that X list thing in that for loop where we were generating the data set, remember?
Mm-hmm.
Yeah, in that, instead of having, so if you see the previous one will look like x underscore list dot append np dot concatenate x comma open square bracket one close square bracket and then temp. Instead of that, I'm defining it in the way that I've put in the chat box.
Okay. Okay.
Okay? Yeah,
Okay.
just try that once. Yeah.
Thanks.
Okay, I'll just quickly go over the rest of the code and we can wrap up the session for the day. Okay, so I had explained what this plot is going to look like, right? So I hope you guys tried it out. But in any case, I'll also go over it. So now let's say I'm picking encoder right, and the lesion is now set to 0. But as maybe I'll put this in full screen. Yeah. Now, as I increase the lesion thing, you'll see that both the arms are struggling more to reach to targets, and both the arms are getting affected by it. Say I make it even worse. It's getting even more difficult for the arm to make movements. Now you can ask me, why is it that in the split brain, the brain is supposed to have two different inputs and two different outputs. So why is it that when I destroy the input layer on side right, why is it affecting both the arms? This is because both of them are going to feed into the shared hidden layers and then later only branch out into the output layer. Now, if suppose instead of it, I go and select the decoder part and I'll put it to 0. Then at baseline level, this is how the outputs are going to look. But if I increase the lesion size, then your left arm is going to show difficulty, whereas your right arm is going to remain the same. This is because the decoder left layer is only connected to the left arm and the decoder. Okay, left layer is not connected to the right arm. This is why it's happening. So even if I completely destroy it, my left arm will be the only one that's affected, while my right arm will remain the same. Whereas this is not how it's going to be when I do it in the integrated brain model. Regardless of the layer that I choose, the lesion is going to affect both the arms because all of the layers there are clumped together. Okay, this is the reason why this is going to happen. Now, once I've created the lesion, I have to now think about what kind of rehabilitation that I can give to the network. Now, we already saw that the data set is created in this way that first it has the 1, 1 condition, then 0, 1, 1, 0, and 0, 0. So here I'm just slicing the data set to have these specifically in different variables. And now based on the therapy that I want to administer, I'll pick that data set and give it to the network and retrain that damaged network on that input. So here I've created the input and stored it here. Then I'm calling the train function and lesion mask I'm defining here. And then in that lesion thing, I'm going to train that network with the data set of my choice. So now based on the data set that you're choosing, it could react differently. So with that, I think I'll conclude the session for now. If you guys have any doubts on this, we can talk about it. If not, then we can conclude the session. If there's anything else that you want to talk about, like if you want to look at more such motor networks and pursue them as like projects or internships or anything, then you can also contact me offline. My number is in the WhatsApp group and the email ID also you guys already have. If nothing else, then we can wrap up the session. Yeah. Mm. Anybody have anything to discuss?
Hello, ma'am.
Hello?
Yes, ma'am.
Yeah.
Is there anything related to like brain signals and neuron signals with like this project? Any
So we're
like
trying
this is
to.
only related to like physical therapy actually. Like we are focusing how we can move our arm physically and how we can train our neurons to give physical therapy. But stroke is kind of EEG signals and MRI signals. Is it related anything to with that?
No, actually, stroke is seen as a physical therapy thing only. In terms of EEG and DBS, we don't really talk much about treatment in that sense. But we are planning on having this motor network but with oscillators involved, so that like you said, we can see how the EEG evolves as the person tries to move, and how it evolves as they make the movement or progress in the movement. So that kind of thing currently we are pursuing. We have a student who's doing his final year project with us, who's working on this. So we just started that project. I don't really have any results that I can discuss yet in it, but yeah, we are pursuing it currently.
Okay, thank you.
Okay, if there's nothing else, then I think we can conclude the session. Thank you so much for joining. I hope you guys also had a good time at the workshop itself. And yeah, all the best and see you guys later. Bye.
Thank you.